first things first, getting into quadrilaterals, we got to talk about one of the most basic ones, which is a parallelogram. Okay, because parallelograms, they make up a lot of different things. They make up rectangles. They make up squares. So what you need to know about a parallelogram is that it has opposite sides that are parallel, hence the name parallelogram. So if I look at BC and AD, I would say that these two lines are parallel. The opposite sides are parallel. Same thing with the other opposite sides, AB and DC. These sides are also parallel. And we just state that with the use of arrows. They show that they're parallel. They go on forever and they never cross. So a parallelogram. And we have all kinds of things that we know about parallelograms, all kinds of theorems here. So here's some of our properties of our parallelograms. Our first theorem, so everything starts, if a quadrilateral is a parallelogram, that's what my little abbreviation here is. So if I have a quadrilateral, if I have a four-sided shape, and I'm saying it's a parallelogram, I know that its opposite sides are congruent. So the opposite sides would be congruent to each other. So the left and the right ones would be congruent, and the top and the bottoms would be congruent to each other. So opposite sides are congruent. There's our first theorem. Our second theorem, well, opposite angles are also congruent. So if I look at opposite angles from each other, those would also be congruent. Just like that. Another theorem, well, this should make sense going back to our consecutive interior angles. If I look, here's a pair of parallel lines, right? Parallel, parallel. If it gets cut by a transversal, what do I know about the consecutive interior angles? They're supplementary, right? So consecutive angles are supplementary. So in this case, I could say that 1 and 2 add up to 180 degrees. I could also say that 1 and 3 add up to 180 degrees. And that should make sense because 2 and 3 are the same, right? So if 1 and 2 add up to 180, 1 and 3 should add up to 180. So any consecutive angles are supplementary. And lastly, if a parallelogram has one right angle, so if I state that a parallelogram has one right angle, then all four angles are right angles because opposite angles are congruent, and then plus the consecutive angles add up to 180, so that would mean these other ones would have to be 90, which in this case would make a rectangle and possibly a square depending on the distances of the sides. So really all squares and rectangles are parallelograms. This we can kind of take from that. So just some properties or some theorems that we can use. So let's use that one. So in the parallelogram, ABCD, suppose B is 32 degrees. I'm just going to draw that in my picture. CD is 80 inches. And BC is 15 inches. So if I use my information, I should be able to come up with my other things I want to know. So AD, well, I know that BC and AD are congruent, so I also know this guy is 15 inches. Just had to look at my picture. Angle C, well, if B is 32, I know that C and B are supplementary because they're consecutive, so they add up to 180. So 32 plus the measure of angle C, I'll just call X, adds up to 180. So if we subtract 32 from 180, we end up with 148. So I know that measure of angle C is 148 degrees. Let's go ahead and write that in there. So I know this is 148, and I already said this is 32. Okay, and measure of angle D, well, opposite angles are congruent, so I know angle D is also 32 degrees. Just using that information. Opposite angles are congruent, opposite sides are congruent, consecutive angles add up to 180. A few more things. If a quadrilateral is a parallelogram again, its diagonals bisect each other. So just be careful. They say bisect each other. They don't bisect the angles, they bisect each other. So that means if these two diagonals that I drew in from B to D and from A to C, they bisect each other. So I know that those two would be congruent to each other and that BP and PD would be congruent. Yeah, that's all I could state. I could say that AP is congruent to PC or CP and BP is congruent to PD. That's all I can state. Okay, they bisect each other. So really, P is kind of the midpoint of each diagonal, isn't it? P is the midpoint. That might come in useful for us later. Also, if a quadrilateral is a parallelogram, then each diagonal separates the parallelogram into two congruent triangles. So if I draw in one diagonal here, I could state that these two triangles are congruent. I could say triangle ABD is congruent to triangle, well, A matches up with C. I gotta put C. Then if I go up to B first, that means we're going down to D in the other triangle. So CDB. So I can say that these two triangles are congruent to each other. Yeah? So just some theorems or some properties with our parallelograms. And let's use that information. Well, if I have a parallelogram, that means I can use all those theorems or properties I just learned. Find the value of the indicated variable. So I'm looking for R first of all. Well, here's a term with R. I know opposite sides are congruent, so I can set those equal. So 4R equals 18. So R equals 4.5. And there's no units of measurement, so I just leave it as 4.5. Looking at S. Well, here's S. Here's another expression with S. I know that diagonals bisect each other, so I know that these two guys are congruent, which means I can set those equal. So I know that 8S equals 7S plus 3. Subtract my 7S, and I get 1S, so I just put S equals 3. So S equals 3 there. It's just asking for the variable. I don't have to plug back in and find angle measures or anything. And lastly, for P, well, let's see where P is at. P degrees. So I'm talking this is 2 times P degrees. Well, boy, how could I figure that guy out? This one's kind of a tough one. You got to look at it. Well, let's think about this here. I know that these two together add up to 58 degrees. So I know that this entire thing right here is 58 degrees. But how would I know if that's 18 or 40 degrees? It's got to be one of those two, isn't it? Well, what was our last theorem there? Remember, if I draw on a diagonal, it splits it into two congruent triangles. So this angle matches up with which angle? This one down here, doesn't it? The 18 degrees. Because if I think of parallel lines here, if I have a parallel and a parallel cut by the transversal going through the middle, aren't those alternate interior angles? Alternate interior, so I know they're equal. So I could set 2P equal to 18. So we got to use some information there. Don't just take a guess at it. So I know that P equals 9. P equals 9. So let's really think about it. How about this? What are the coordinates of the intersection of the diagonals of a parallelogram, MNPR? With vertices, okay, I already got this graph. The intersection of the diagonals. Well, if I think about this, if I draw on one diagonal and another diagonal, I know they're going to meet somewhere in there. Okay, my first thought is, intersection of lines, that I need two equations of lines to set up a system of equations. That always takes a lot of work, doesn't it? Like we did with, our ortho center and all those different things. Is there an easier way? There's got to be an easier way, isn't there? Well, what did we say earlier? The intersection is also the midpoint, isn't it? And how do you find the midpoint of 2 points? Just the average of the x's, right? And the average of the y's. So you basically add the x's, add the y's, divide by 2. So I can find the midpoint. Just pick two of the points to find the midpoint right here. So if I found the midpoint of NR, that should be where they meet. Okay? So let's find the midpoint of NR. I'm just going to call it A for now. I'm going to call it A. So if I'm looking at A, so I add the x's. So N is -1. And the x for R is 3. So 1 plus 3. And I divide by 2. Right? Add them up, divide by how many there are. Then I add the y's. So in this case, 3 plus 1. So 3 plus 1 divided by 2. And that should be my point, the midpoint for the midpoint. So -1 plus 3 is 2. 2 divided by 2 is 1. And 3 plus 1 is 4. 4 divided by 2 is 2. So this vertex is at 1, 2, where those diagonals meet. Okay, much easier than trying to find two equations aligned to set up a system. Okay, so if you can understand that the diagonals are basically the midpoint where they intersect, and the midpoint of each diagonal, then it makes it much easier. Last thing, we got a proof for you. Yeah, but it's going to be a lot easier than we think, though. So one, start with my given here. I'm going to bring that down. Second step. Remember we always talk about use your given. You don't even need to look at what you're trying to prove yet. Just use your given. Well, they say they're parallelograms. So what do I know about parallelograms? A lot of things. Opposite sides are congruent. Opposite sides are parallel. Opposite angles are congruent. Consecutive angles add up to 180. All kinds of things. So depending on which one that I want to use, I probably should look to see what I'm trying to prove now. So I'm trying to say that Wx is congruent to YZ, or ZY. Well, if I think about it, these two parallelograms share this side right here, don't they? That VT. Well, and Wx and YZ should both be congruent to that because they're opposite sides of the parallelograms. So that's what I'm going with. I want to use something with the opposite sides. So I haven't stated these two are congruent yet, Wx and Zy. So first things first, if I look at this blue parallelogram, it said it's a parallelogram, so I can say that the opposite sides are congruent. And all I want to deal with is these two, don't I? I don't need to bring anything else into play. I could, but it's just a waste of time. And I'm going to say Zy instead of Yz because that's what I'm trying to prove up there. So Zy is congruent to Vt. And that is, well, that's just our parallel. Like I could go back and look at the theorem, the exact theorem, right? Theorem 6 point whatever, or state what's actually happening. Or I could just say definition of a parallelogram. And if you want to draw a little picture like this, if you don't like writing out parallelogram, I don't care. Just something that I know. Or if you want to put para with a period, that's okay too. I'll just write it out for this part. Definition of a parallelogram. Well, I could also throw this one in that same reasoning, that Wx is congruent to Vt as well. I can put that in the same one since I'm using the same reasoning. Is congruent to Vt. And let's be consistent since I use Vt here. Let's use Vt there. And I want to use Wx because that's in what I'm trying to prove. And I got the same reasoning, so I don't need to change anything. Don't need to put a new reasoning step. Well, lastly, they're both congruent to Vt, aren't they? What I'm trying to prove. So I could state that Wx is congruent to Zy in a couple different ways. I could either say substitution, or I could say they're both congruent to the same thing, which makes it the transitive property. I like the transitive property, right? If A equals B and B equals C, A equals C. So I'm going to say transitive property. Or substitution, doesn't matter. Say, that wasn't so bad, right? You got all freaked out because it was a proof, but really once you just thought about it for a second, not too bad. All right, just a little information on your parallelogram.